This video is the second video for going to infinity. The first examples here you're going to work through on page 1 and 2. You're going to work through on your own. You're going to try and draw some graphs, y equals 3 or y equals 1 over x. And again, just review going to infinity on those. Again, work on the idea that when you graph a constant, the answer in infinity is constant. When you graph a rational, the answer should be 1 over infinity, or 2 over infinity is going to be 0. The connection then to past learning is we did sequences in Math 20-1, and we talked about going to infinity with these sequences. And again, whether it's 1 over r or 1 over x, which is a rational function, those things have the same mathematical properties. So we want you to kind of work through these examples here as well. The second part of infinite sequences is you don't always have just 1 over n or 1 over r. Sometimes you have a more complicated rational expression, so you can do a table of values, plot some points, and then basically figure out what's the math that we use to justify the answer. And it's going to come back to what we did before. How do you get constants and rational functions into the numerator and denominator of your expression so you can get to work with constant terms and zero terms? And that's what we're going to show you and on page 3. We'll do a couple of examples for you here, but we want you to try to understand that what you're working on are two principles. How do you put a constant in, and how do you get a rational function out of this? Again, these only work if your ratio is convergent. Your sequences, your series have to come together. The last term needs to be approaching a specific number. So when you start looking at the examples we have here, a question like number 2 is very much like what you just did on the previous page. You have 2n minus 3 over n. I want to try and figure out what's the math where I get to change this to be a rational function in the top and constant terms in the top, rational function in the bottom or constant terms in the bottom. And the way you do that is the reverse of what you did before. Before you try to take fractions out of questions, now we're going to put fractions into questions. I'm going to multiply by 1 over n to both the top and bottom of this limited expression. Again, it's a little bit of math here. 2n times 1 over n is going to give me a constant term of 2. 3 times 1 over n is 3 over n. N times 1 over n, n times its reciprocal is 1. When I look at this information I have now, I can put infinity in. I couldn't put infinity in to begin with because infinity in the original expression was 2n minus 3. If you graph y equals 2x minus 3, there is no answer at infinity. If you graph y equals x, there is no answer at infinity. Right? Infinity is not a defined number. If we put an infinity in now, we kind of showed with our examples, the constant term, when you graph it, doesn't change at infinity. So the 2 doesn't change and the 1 doesn't change at infinity. You're graphing constant terms. What happens when you graph 3 over infinity? At the very end, you get 0. So this is the math that you use to justify that the last term, or the infinity term, is going to be 2. So that's the idea. Doesn't matter which example we pick. As long as we know that we can put in rational numbers or rational functions and constant terms, we can find an answer. Question like 4b will not work. It's not convergent. Positive 1, negative 1, positive 1, negative 1. They're not approaching anything. There's not a number that's being approached. So something like b, there is no limit. If we look at a question like 4a or 4c or 4d, what we have to be able to do now is either by graphing or algebraically figure what the answer is going to be. If we do a question like 4c, this is like Goldilocks and the 3 bears. You got to pick the right side rational expression to put in. If you don't use a large enough degree rational expression, you still end up with like a linear function or quadratic function that has no answer at infinity. If you pick too big of a degree, all you have in your answer is a bunch of zeros. And you don't want to have too many zeros because 0 on the bottom is undefined as well. Right? You can't divide by 0. So we've got to figure out what is the best to put in this thing. And so we got to figure out degrees. We're going to use the 4th degree because that's the highest degree in the question. If I go to simplify this limit expression now, if I put n to the 4th under 6n cubed, that gives me 6 over n. 3 of the n's cancel with 4 of the n's. If I put 1 over n to the fourth, that doesn't simplify. If I put 3n to the fourth over n to the fourth, I got a constant term of 3. If I put n over n to the fourth, I get 1 over n cubed. So I'm just doing a whole bunch of exponent law skills questions. I'm doing multiplying with distributive property kind of questions. And now I want to put infinity in because I can. 6 over infinity, 0. 1 over infinity, 0. 3 is the constant. It does not change. 1 over infinity, 0. This gives me 0 divided by 3, and that's an okay thing in math. We can divide by 3, we just can't divide by 0. So 0 divided by 3 is 0. So as this graph goes closer and closer to infinity, you can get closer and closer to the number 0. So that's what you're going to do. On page 50 here, you got questions 1 to 6 and number 8. You want to be able to use the constant term skills and your rational function skills to evaluate limits at infinity.